So what's the main idea of a derivative? Let's go ahead and learn about it. And this is a really important concept. So what we learned before was we learned how to find the slope between 2 points. And you're probably thinking, Mr. Underholt, what's going on? Why are we finding the slope at 1 point? How do we do that? I thought I could only do it between 2 points. And it's true, you can only do it between 2 points until we use a limit. And that's the whole point of limits, is that we now could find the slope at 1 point, at a point, instead of at 2 different points. So if you look at this graph, usually we find the slope between 2 points, right? And so what is that slope? Well, that slope is y2 minus y1 over x2 minus x1. Well, that's just fancy talk for f of b, or that's basic talk for f of b minus f of a over b minus a. This is the fancy talk here, right? So what if we're able to take the limit as a approaches b of this, or b approaches a, whatever it is. In other words, remember a limit, we're taking a value and we're getting infinitesimally close to another value. What if we can take 1 point, basically, like let's just say we have these 2 points, and I'm going to take this point and apply a limit to this one and send it that way to where the point gets so close to it that you basically get an instantaneous rate of change. Not that you actually do get it, because the limit will get you there. So let me open up a different Desmos graph than I did before, just to show you the secant line, right? The secant line is the slope between 2 points. So what if I'm able to take this point and I just drag it until we get right to this point? Look at that. Now we have a tangent line. We have the slope at that particular point. So that's the idea. We're going to take this point and just drag it to where it's going right that way. And the way we're going to do it is using a limit. So there's 2 different definitions of limit. There's just this classic way. That's the whole y2 minus y1 over x minus x1. Remember, this is called the difference quotient. So that is this one here. And I should use some different colors just so we can kind of distinguish the difference here. Or let me put that blue. It's kind of hard to see just this part. So we have this one. This is one definition of derivative. And so it's just applying the limit as x approaches t. This is the way Kahn writes it. So limit as x approaches t. And this is the slope at a particular spot, whatever t is, not just for a general x. Limit as x approaches some number of f of x minus f of t over x minus t. So what's going to happen is this number is going to get really, really close to whatever x is. So that's going to be kind of nice. That's going to work out for us. Then we have this other one. So where does this one come from? We have this whole t plus h idea minus f of t over h. A little bit different way that it looks, but this is also another definition. It's actually a more popular definition. It's easier for the general algebra when we get there compared to slope at a point. This one kind of works out nicely, and you'll see that in the future one. So the idea here is, instead of calling this a and this is b, you know, and just using like, instead this would be a and f, or this currently is b and f of b, and this one was a f of a. You know, that's how I wrote this one right here, right? We had our 2 points, which is f of b minus f of a over b minus a. Instead, let's just say that a is x and b is x plus some value. In their case, they're calling it delta x, meaning change in x, right? So it's the same idea. This is just x, some number, and then this is that same number plus something else. And so I'm just going to substitute that right into that difference quotient. So we'll have f of x plus delta x, that's for b, minus f of a, well, we changed a to x, didn't we? All over b is x plus delta x minus a is x. And if we simplify this, the x cancels out and we're left with delta x. Now, one of the things that they do here, instead of delta x, they just decided to change it to an h. Not sure why. You can ask the math gods. So instead of delta x, we'll call it h. It's just more or less, not doing some sort of formal proof. I just want to kind of give you a general idea of where these formulas are coming from. They all just come from the slope formula. And then that limit, this case was delta x going to 0. If you think about it, what would happen if b approached a or a approached b? This would go to 0, right? So h is going to go to 0. Now that brings a complication because, well, we can't divide by 0. So that's going to be the difficulty of finding derivatives, is that this limit generally isn't the easiest limit because the bottom is always set up to go to 0, which is why we did the whole factoring and canceling and all that in the first place with limits, was to build up to this. So the idea, once again, the main idea that you get from this is that formula comes from taking 2 points, which is how we normally find slope, and getting one to approach the other. That's the main idea. We're doing that using a limit. So how would we set this up? Let's go ahead and look at this one. So there's 2 different ways you could set it up. So you got to keep your eye out for both of these forms. Now, if they just have an h in the bottom, then you know, like this one, h in the bottom, it's going to be rolling with this form. Compared to if they have like x minus something, 2 things subtracting on the bottom, then you know they're going to be using this form. A lot of people are like, I don't know which one to use. Well, look at the multiple choice and you can see, like this one's all h, but then look right here. X minus 2. That's not an h in the bottom. So obviously we're going to try to make it fit this form here, right? So let's go ahead and learn how to substitute this. That's like the start for this. So we're going to evaluate f prime of e using, if you can see, the one with the h on the bottom. So it's just going to substitute an e in for the t. So f of t, or f of e in this case, f of e would be, well, if f of x was e to the x, and sometimes the most complicated part is just this part right here, honestly. It's usually where the struggle comes from. This is the part I had to break past before this made sense. So we'll go over that in a little bit. So what is f of e? Well, f of e, well, f of x is e to the x, so f of e would be e to the e. Sounds crazy. And then we also need to know what is f of t plus h. In this case, remember, e is t, so f of e plus h. Notice this is f of t plus h. So it's basically, you know, t is going to be e, like I said. That input's going to be e. So we need to find out what is f of e plus h. Don't overcomplicate this. We replaced the x with an e. That's how we got that, right? What do you think happens when we replace the x with an e plus h? We're just going to have e to the x. Or not e to the x. E to the e plus h. So all we did was we took whatever was on the inside, we just put it in there with for the x. So this input here, I just replaced the x with whatever this was. So once again, if I had f of pizza, then you better believe all I do is switch the x with a pizza. So it's e to the pizza. That's what's going on with this. So if it's an e plus h, I just switch the x with an e plus h. Don't overcomplicate that. Don't run that through your head like it's the craziest thing you've ever seen in your life, as I did. So let me show you what's going on. So running right here with this formula, it would be f of e plus h minus f of e over h. And we did all the hard work. F of e plus h is e to the e plus h. Kind of sounds crazy. I'm getting things mixed up here. Minus e to the e is our f of e, right? F of e was e to the e, so I changed that out with e to the e, over h. And so I'm just going to go ahead and look for this. And my division sign just gets worse and worse. That wasn't bad. So looking for this one here. And I found it. This one seems good, just to double check the others. This is missing e to the e. Look at this. This should be e to the e plus h, right? This one says x plus h. So you just want to double check that. Don't want you to get it wrong for that reason. All right, let's look at another one. So once again, limit as h goes to 0. It's got to be the longest lesson of the year, but an important one. And it's going to be g of 3 plus h minus g of 3 over h. So if g of x is x squared, then g of 3 is 3 squared, which we know is 9. And g of 3 plus h is 3 plus h squared. We'll just leave it like that. I mean, we could FOIL it out if we needed to. And so substitute that into here. So g prime of 3 equals, limit as h goes to 0, of 3 plus h squared minus 9 over h. And we'll just go ahead and look for that. 3 plus h squared minus 9 over h. That one looks good. Just double check the other. 3 plus x. Nope, 3 plus h. Okay, minus h squared. No, that makes no sense. All right. This one's taking on that definition. The classic definition here. That whole y2 minus y1. So let's focus on this. Limit is x. Oh, I'm missing a part. That's right, it's a limit. Otherwise, it wouldn't be an instantaneous rate of change if we didn't apply this. It would be an average rate of change. So x is approaching t. So this is an immediate indicator of what t is. It's going to be 2. You can see it in different places, though. Right here and right here. See, t is right there. Those would be the quick ways to pick that up. So in our case, it's 2. So this is good. Now let's figure out what g of x is. Well, g of x is located on the left right there, right? So g of x would be x squared. So we're going to go with this one. And it makes sense g of t, well, if g of x was x squared, then g of 2 would be 2 squared, which would be 4. So it does make sense. It fits that mold real well. This one's cosine. Don't fear it. You can see right away that 0 is what we're trying to find that derivative at. And then our function is just cosine of x. You know, cosine of x minus, just takes that same form. So don't overthink these. That's the worst thing you can do. Just fits that mold. Sorry for the long lesson.